recording, blah, blah, blah. Let's turn that on. How many of you have heard of buffers before? Maybe took a biology class, heard of them? Okay. A buffer is a solution which resists changes in pH. And it resists a change in pH when you add a small amount of strong acid or strong base. Okay, so it minimizes the change in pH. So we're going to start with a solution which is not a buffer. We're going to start with 1 molar acetic acid, not a buffer. It's just an acid. We have our equilibrium, okay, 1, 0, 0, plus x, minus x. And if we do the calculations, we end up with a concentration of 0.4 and 0.4 and approximately 1, because 1.0 minus 0.004 is equal to 1, correct? Yes, all right. So here's our first question. Will the shifting of this equilibrium, be able to shift to bring hydrogen back to close to the original if we add some NaOH? So let's think about this. Equilibrium CH3, COOH, la 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 la, H plus, Noah, shh. CH3COO minus, we add some NaOH. Think about whether that equilibrium will be able to shift. And in fact, I want it up here. If we add NaOH, because then we've got the numbers in front of us. Will it? If we add OH minus, what happens? It'll become more basic, but what happens in terms of the species in the equilibrium? Does OH react with any of those things? Reacts with H, what? H3O, okay? So our OH minus reacts with our H3O plus. Those two get together, and what do they make? They make water. And therefore, what happens to our concentration of H3O plus? H3O plus decreases. And if it decreases, which way would the equilibrium need to shift to bring the H3O plus back up? Needs to shift right to bring concentration of H3O plus back up. If we're starting with 1 molar, is this equilibrium able to shift to the right? Is there enough reactant that we can do that? I have 1 molar CH3COOH. Does that give us enough to shift to the right? Yeah. Remember, how much are we adding? A small amount. Okay, we're not adding like, buckets and buckets. We're adding a small amount. So we've added a small amount of NaOH to this solution. So do we have enough of that to shift to the right? No? Is a small amount more than 1? Oh, we have enough. Why did you shake your head then? You said no. You're confusing me, Alexander. Okay, so yes, there is enough CH3COOH to shift. Now, what if we add HCl? Oh, and it even says how much. It says 0.1 mole of NaOH. 0.1 mole of NaOH. We only need to really replace 0.1 mole, and we have 1 mole of the other stuff. Yes? So would it be okay? Yes. Now, what if we add 0.1 mole of HCl? So now what we're doing is we are which way will this equilibrium shift? It'll shift to the left. And we went from 0.004, we went up to 0.104. Will we be able to shift left enough to bring this number back down to that, given that we have that much of the base? No. Okay, we've only got a very little bit amount of the base, so we cannot shift left enough. There is only 0.004 moles of CH3COO minus, which is not enough to deal with the extra 0.1 mole. Of H plus. We're going to run out of it. Yes? I feel like I could fix this and give more space. Fix more space. Okay. Now what we're going to do is we're not just going to put in acetic acid. Okay? All we put in there was acetic acid. Now we are going to add both. Yes. Uh-huh. How do I know it's shifting to the left? Because it increases the concentration of H3O plus. HCl, because it's an acid. Well, yes, it is. Because no, but look, it's shifting, it's reacting with it as it shifts. Because the H3O plus is a reactant in the reaction. You don't have to look at how it affects other things. It is directly here. H is H3O plus. Yeah? Yeah? Okay, cool. We only have to look at how it affects things indirectly if that species is not specifically in the equation itself. Yeah, good question. Okay, so now we have added some. We have our acetic acid, and we have 1 molar, and we have our CH3COO minus, and it is also approximately 1 molar. So what we've done is we've added some NaCH3COO. When we add this to this equilibrium, the CH3COO goes up. Yeah, I definitely need more space for this. I need like 3 of these diagrams. this goes up and it's going to shift it that way, yes? If we add acetate, yes? So what will happen is if we add 1 molar of this, it's going to cause a shift that way, which is going to give us a little bit more than 1 molar. And this will be, because we've added 1 molar, this will be a little bit less than 1 molar. But the moral of the story is that they're pretty close to 1 molar and pretty close to 1 molar. Because we have shifted to the, oh well, let's go through this process. We added acetate, so the acetate concentration goes up, so the system shifts left, which causes hydronium to increase or decrease? Decrease, and acetic acid to increase. Yeah, definitely need more space here. That's okay. The solution now has both a relatively high concentration of weak acid, approximately 1.0 molar, and a relatively high concentration of the weak base, approximately 1.0 molar. And our hydrogen concentration, hydronium ion concentration, is very low. What will happen when we add 0.1 moles of NaOH? We'll do this one in blue. 0.1 moles of NaOH causes the shift, right? It's going to cause a shift to the right, because this causes a decrease in H3O+. Are we able to shift to the right? Do we have enough of this to shift to the right? Yes. If we add some HCl, this one I'm going to do in red. If we add some HCl to that solution, what does that cause? It causes an increase in the concentration of H3O+, which is going to cause a shift left. And now this time we don't have a small concentration here. We now have a pretty large concentration of acetate. So can we shift to the left? Yes. So the solution is now able to resist a change in pH, which is what a buffer does. And it can do it both when we added a strong acid and when we added a strong base. The previous solution, the one that was only acetic acid, was not a buffer, because although it could resist a change in pH when you added a strong base, it could not do it if you added a strong acid, okay? A buffer has to be able to do both. And now I sometimes get the question, we've just mixed an acid and a base together, don't they just neutralize each other? The answer is no. Remember, for neutralization, what do you need? You need one of the two of the pair to be strong. Yes, both of these guys are weak, so they just form an equilibrium. There's no neutralization. So in neutralization, you need either a strong acid or a strong base, or both. If you mix a weak acid and a weak base, they just hang out in equilibrium. And this equilibrium allows the buffer to use up most of the extra H3O plus, or to produce more H3O plus when a strong base is added. So describe the stress, the shift, and the overall change in concentration of H3O plus, and the overall change in pH when each of the following is added to the buffer system. When we add HCl, what is the stress? Yeah, increase in concentration of H3O plus. So the shift is to the left. And so what will be the overall change in the concentration of hydronium? It will be higher. Will it be a lot higher or a little bit higher? It'll be a little bit higher. Because remember, the stress brings it up, and then the shift brings it back down. Not to quite where it got to. We're going to have graphs in a moment, so I won't draw it here. Okay, but it's like up and then down, but not quite to where it got to before. And what happens to our overall change in pH? It is a little lower. But not much. Okay, we've minimized the change. By the shifting. If we add NaOH, what is the stress? A decrease in the concentration of H3O plus, yes indeed. And so we shift to the right. And if we shift to the right, the overall H3O plus, it went down, but now we're making more, so it ends up a little bit lower. And the overall pH ends up being a little higher. And that's all there is to a buffer, okay? So really, there's not much here. This is all blah, blah, blah that we've already talked about. This is what we've got in terms of a graph. Okay, so this is our concentration of H3O plus in a buffer system. The H3O plus, we added HCl right here, and the H3O plus spiked, and then we get a shift to the left, and that brings the H3O plus back down, and it ends up being a very small amount bigger than it was before. Okay, so if you're looking for the graph, that's what that concentration graph will look like for hydronium. Let's draw a graph of pH versus time. Could you do that? I'll give you a hint, it starts as a straight line until we add the HCl. See if you can draw it.
It is higher, slightly higher. Who knows, that might be wrong. It's not supposed to be down on tires. Yes.
How much did it raise the hydronium concentration? A lot. How much going to be? A lot.
But yeah, it's just that, as the scene, and be longer. Yeah, like a one, I mean, not one. There's 30 episodes.
This goes up. Then what happens after it goes out? I mean, I guess they're all moving, so that this goes down and then one move. Yes. Well, they start off somewhere, it doesn't really matter where. Oh, so like it can start like this. Well, you're gonna start off somewhere, and then what's gonna happen to the pH when you add the HCl? It's going down. Yeah, pH goes, pH goes up, pH goes. What is the number? So remember, if hydrogen goes up, if hydrogen ion concentration goes up, then pH must go down. And then what happens is that hydrogen goes down, so pH must go up. Where does it end up? A little bit higher or lower? A little bit lower than it was before. Okay? Because here we had our shift to the left, uses up H3O plus. Therefore, the pH increases. All right. Let's do the next one. So here we have our same buffer solution. This time we are going to add some OH. What does OH do to the hydronium ion concentration? OH causes a decrease, which causes the system to shift to the right. And as it shifts to the right, what happens to the hydronium ion concentration? It goes, so it went down, and as it shifts to the right, it goes up. So we can show that graph here. It goes down when we add the NaOH, and then we have our shift right. And that makes more H3O plus. So we have our OH minus using up the H3O plus, and then we shift to the right and we make more H3O plus. And remember, this curve is still just H3O plus. We're not looking at the actual concentration of hydroxide, okay? We could look at that, but we're not. And then once you've got that, I imagine that down below there is a graph showing pH. Am I correct? Why don't you fill that in?
Oh. I would make it like a little bit higher. Yeah, just so it's more obvious, like it is higher, but I would make it one of our. Okay, good stuff.
Okay, so here we are. We have our pH. NaOH is added, so the pH goes up. And then it comes back down, but it doesn't quite get to where it was before. Is good? Okay. Remember when we had only the weak acid? Was that system able to buffer effectively? No, because if we added a small amount of OH, excuse me, OH reacts with hydronium, the H3O plus has decreased. Can the system shift to make more H3O? This is what I was wanting on the first page. Why am I repeating it? Anyway, I need to really rearrange this particular worksheet here. Can the system shift to make more H3O plus? Yes. And that's because there is lots of acetic acid, about 1 molar. But when we added H3O plus, when we added HCl, H3O plus has increased. Can the system shift to use up that extra H3O plus? No, because the concentration of the base is low. Excuse me. So the system is not able to minimize a pH change upon the small amount of acid being added, so it is not an effective buffer. I should know better than to drink or eat when I'm teaching. Because once it's irritated, it just... Okay, so key point. If you have a buffer system, you have to have a relatively large concentration of both the weak acid and its conjugate base. Can't just have one or the other, has to be both. Yes, so you have to see what it is at your particular pH. Does that make sense? Yeah. No, but that's a good question. Okay, so it is not enough to add the weak acid, you have to add the weak base. Is it possible to go into the back room and get a bottle of acetate ions? No. What do you think we should pair with acetate? Something that's soluble with everything. What's a good cation that's soluble with everything? Na. And it won't hydrolyze either. Yes? So choose something like Na or K. So what you need is to make a buffer. You need to add the weak acid plus the salt of the conjugate base. Okay, so it'll be like Na whatever. And how do we abbreviate this? WASCABA. Weak acid plus the salt of the conjugate base, Wascaba. Okay? So if you want a buffer, you want Wascaba, a weak acid, and the salt of its conjugate base. Another way to make it, can you guess what another way to make it? If you could make it from a weak acid and the salt of its conjugate base, what else could you use? You could use a weak base and the salt of its conjugate acid, a Wubska. Yes. So a buffer is either a mixture of a weak acid and the salt of its conjugate base, or a weak base and the salt of its conjugate acid. And you have to have relatively large concentrations of both. In the context of chemistry 12, relatively large can generally be taken to mean greater than or equal to, why has this stopped working? Greater than or equal to 0.1 molar. But that's not a hard and fast rule. Sometimes you'll see a big buffer made out of like 0.05 molar this and 0.05 molar that. Okay. Relatively large, greater than or equal to 0.1. Don't worry about it too much. It'll be obvious. It'll be somewhere in the multiple choice and it'll have concentrations like 0.0001 or 1. And you'll be like, ooh, that one, right? It'll be comparatively obvious. Now, to be honest, I actually don't like this, but this is how Chem 12 teaches this. So I will teach it to you this way, but it makes me sad. Anyway, in general, if you want an acidic buffer, one that buffers at a pH less than 7, that's what we call an acidic buffer. You will want the weak acid and the salt of its conjugate base. So for example, you might take HCN, which is the weak acid. Who is its conjugate base? CN minus. How do we make that a salt? Add an Na to it. So now we have NaCN and we have HCN. And if the HCN is about 0.5 molar, what concentration do we want approximately for the NaCN? About 0.5 molar. Okay? Relatively high and relatively equal. I'll say close to equal. Could you please write the equation for the equilibrium? And let's make this the net ionic equation. For the equilibrium formed by the above buffer system, and I would like you to include water, please. So you're going to be writing the net ionic equation for this, the equilibrium formed by the buffer when you have HCN and CN minus. and you're going to include water. See if you can do that.
But basically what you have is you start with a weak acid. And then the weak acid will allow it to shift. You've got a lot of it, that allows it to shift this way. But if we add some base, or sorry, if we add some acid, this can't really shift this way because we're going to run it. So we're going to make it fun.
The hour watching this.
Wow. So you put HCN. And a high concentration. So into your solution, you might get a protease and you put in 1 mole of this. Two things, yeah, it's always going to be acid and both of us.
Okay, let's go. I think I got it. I don't know. Oh, yeah.
If you've got HCN on one side, where does this one get other sides? What's the difference? Actually, why you write down that are like highlighted if you wanted that. And I'm thinking which means you get rid of the sodium. And what else? What do you do? I think from there you can probably do it with the lots. Your lots. Feel free to stay for the okay. You have an acid and its conjugate base. When you have an acid and its conjugate base, do they go on the same side of the equation or do they go on opposite sides of the equation? Conjugate acid-base pairs go on opposite sides. So we have HCN on one side and we have on the other side what? CN minus. And what else did I say to include? Water. So where shall we put the water? Let's put it on the left side, okay? H2O. And that will give us HCN plus H2O gives CN minus plus H3O plus. Now, to be honest with you, you could have written this a different way. You could have put the CN minus on the left and the HCN on the right. And if you did that, you could put the water on the left and the HCN on the right. And what would we get over here?
Oh, wait.
OH minus. Both of those represent just they're two sides of the same coin. Have you heard that expression? Two sides of the same coin. They basically mean the same thing. It's just like looking at it from one direction or looking at it from the other direction. Okay? Usually, though, if you're doing an acid, I would just stick with this one because it's less confusing. Yes? I think that just makes less confusing. Now, in general, if you want a basic buffer, one that buffers at pH greater than 7, then you will use a what? When we wanted an acidic an acidic buffer, we used a weak acid. When we want a basic buffer, buffering greater than 7, we want a weak base. And what do we put with it?
A conjugate. I mean, oh,
We want its conjugate acid, but we don't just want the conjugate acid, we want the salt of the conjugate acid. So we want the WUBSCA. So this was WASCABA, and this is WUBSCA. So who is our weak base here? For our example, we have NH3, ammonia. And we need to pair, its conjugate acid is NH4 plus. Who could we put it with that will not hydrolyze? What anion could we pair it up with to make it into a salt?
but isn't that one of the ingredient ones?
Yes, but I want to pair it with something that will not hydrolyze. This will hydrolyze.
I'll make it.
I want it to be paired with an anion because it needs to be a salt. Yes, we've got our positive ion. What I'm saying is what's going to be our negative ion that it goes with.
Yeah.
You could use Cl. Anything else? Br? Anything else? NO3. Those are the big ones, right? Those are the most common ones that you'll come across. I mean, there's I as well, and then there's ClO4, but we're not going to worry about that. So in this case, I chose to put it with chloride, but you could easily put it with bromide or nitrate because they are the conjugate bases of strong acids. They will not hydrolyze. And now we have NH4Cl. What concentration would we want that to be? We'd want it to be about 0.7 molar. So literally when you make a buffer, you take your water and you would dump in, if this is 1 liter, you would dump in 0.7 moles of NH3. And separately, you would dump in 0.7 moles of NH4Cl, and that would give you the buffer. Buffer is made of both. B for buffer, B for both. I will not do that again. Once was enough. You missed it yesterday. Write the equation for the equilibrium formed by the above buffer system. I would recommend when you're looking for the equilibrium, would you be wanting to write the formula equation or the net ionic equation? Net ionic. And who should be one of the reactants? H2O should be a reactant. Give that a go. This actually can't happen because that is a strong base. No. Can you make a strong base? Nope. No, I'll show you the word. No. One side. Okay, so the NH3 goes on one side and the NH4 goes on the other side, right? Because the conjugate acid and base go on opposite sides. So one way of writing it would be to put the NH3 on the left and the NH4 on the right. What happened to the chloride? Where'd it go? It's a spectator, so I'm leaving it out, okay? And remember, we want water to be a reactant. So if we put NH3 on the left and we make water a reactant, then we get NH4 plus. Who is our other product? OH minus. And bear in mind that your charge on both sides should be equal. It's a total of 0 charge on the left and a total of 0 charge on the right because you have a plus and a minus. Our other option would be to put the NH4 on the left and the NH3 on the right. And if we do that and we put our water here, then we'll end up with H3O plus. Okay? For AP, we would go into the math. And you would actually see that you can use a weak acid to make a basic buffer and a weak base to make an acidic buffer. It just depends on their Ka and Kb values, what they're really good at doing. But for Chem 12, if you want to make an acidic buffer, use a weak acid and the salt of the conjugate base. And for a basic buffer, use a weak base and the salt of the conjugate acid. Okay? There's actually not a lot to buffers for Chem 12. All right, you just need to know what they are. So, before we move on, please define a buffer for your partner. We defined it earlier on, see if you can remember.
And also with weights. That works. Solution that minimizes with the
A solution that minimizes the change in pH when a small amount of what is added? Strong acid or strong base. Because you're really adding H or OH. Yeah? And if you want an acidic buffer, what does it mean to be an acidic buffer? It keeps the pH constant. Yep. Keeps pH constant at less than 7. And what would we use to make an acidic buffer? WBSCA or WASCABA? WASCABA. And if we want to make a basic buffer, first of all, what's it going to do? It's going to keep pH constant at greater than 7. And that one is going to be made of WBSCA. And that's almost all there is to know, other than the fact that you need a high concentration of both things. Now, if I was really, really being honest with you, then I would tell you that if you really want to know at what pH a particular acid can buffer, or at what pH a particular base can buffer, we would look at our data booklet and we would say the Ka of acetic acid is 1.8 times 10 to the negative 5. Yes? And what that means is that it is going to be good at buffering at around pH 5. Okay? And the reason for that, and if you remember from yesterday or from the day before, because we actually did this the day before yesterday, do you remember when we were at the half equivalence point? What is true at the half equivalence point? Concentration of, first of all, concentration of HA is equal to concentration of A minus, because you've taken half of the HA, which is what you started with. Say you started with 10 moles of HA. You have neutralized half of it. So now you have 5 moles of the HA left and you have 5 moles of A minus. Okay, so that's at the half equivalence point. You've neutralized half the acid. Those two concentrations are equal. And if those two concentrations are equal, then your Ka, which is H plus times A minus over HA, what can we do there? We can cancel those out, yes, because they are approximately the same. When else do we have the concentration of a weak acid and its conjugate base approximately the same? Under what other situation do we have the concentration of a weak acid and the concentration of the conjugate base approximately the same? There's actually 2 situations, but one that we did today. Or actually, we'll leave even one better. Oh, we'll do this one. Here we go. They're relatively close to each other when we have a buffer. Okay, in a buffer, they're going to be relatively close. So what that means is that the hydrogen ion concentration is going to be equal to the Ka, which means that the pH is going to be close to the pKa. And how do we find a pKa? Negative log of Ka, which would give us approximately negative log of 1.8 times 10 to the negative 5 is going to be somewhere in the neighborhood of 5. It's probably going to be a little bit closer to 4 than 5. You could figure out exactly what it is. You could be like, okay, what is the negative log? Do you have a calculator here?
Does it work for the other ones too?
Yeah, it works for all the other ones, right? So you could say, I would like to be a buffer close to pH 10. So actually, the example that I gave you where we used HCN would actually be much better at buffering close to pH 10. But apparently you're not supposed to know that in grade 12. I feel like I need to go through and change that, but I'm only teaching for Chem 12 2 times more after this. So yeah, because I alternate with Ms. Wu. When we teach the 11 enriched, generally we teach 11s just to kind of make life easier. And then when we teach Chem 12, the AP Chem 12, we teach the grade 12s, just again to make it easier. Yeah, and so, but there we are. So I'm not too excited about making lots of changes, but I think I should make that change because It's doing you a disservice, I think. On the other hand, all my tests are set up that way, so whatever. Yeah. Okay, anywho, that's not what we wanted. We wanted that one. There we go. Okay. All right, buffer capacity. Oh yeah, we have to do buffer capacity. What just happened here? I just tried to make it bigger and that didn't work. Okay, come back. Buffer capacity. The capacity means that if you don't have enough of the weak acid or enough of the weak base, you can use up all of it and then the buffer will stop working. That's why I said they have to be at relatively high concentrations. So a buffer's capacity, you will reach the buffer capacity when you use up all of one of the weak acid or the weak base. This is known as the capacity of the buffer or the limit of the buffer. Once you have used up your reactants, you cannot shift further to the products. Once you've used up all the product, you cannot shift further towards the reactants. So it is limited by the number of moles of the weak acid, and it is limited by the moles of the weak base. The more moles you have, the longer it can buffer for, the more acid it can absorb, or the more base it can absorb. Yes? The lower the number of moles, the less acid it can absorb and the less base it can absorb. So higher moles, higher capacity, lower moles, lower capacity. So this is the kind of question you might run across. Which of the following 1 liter solutions has the greatest buffering capacity?
The one with the most moles.
The one with the most moles, and they're all 1 liter solutions, so we don't have to worry about volume being a factor. Probably B, yeah, because all the other ones, they're a lot lower. We've got our highest concentration here and our highest concentration here. That gives us the greatest number of moles of acid and the greatest number of moles of base. Anyone confused about what we mean by buffering capacity? Would like me to explain it in a different way or anything? No, we're good? Okay, excellent. So let's say we have our buffer solution is prepared using 1 molar acetic acid and 1 molar NaCH3COO. And we are going to use 1 liter of our buffer. How many moles of CH3COOH does that give us? If we have 1 liter of 1 molar CH3COOH, how many moles of CH3COOH do we have? And we got 1 liter. So how many moles? 1 mole. How much of our base do we have? How much CH3COO minus do we have? Also 1 mole. And now we're going to add 1.5 moles of HCl. Is this within the buffer's capacity, or have we gone past the buffer's capacity or past the buffer's limit? We exceeded it because we only have 1 mole of base to react with all the 1.5 moles of acid. So we're going to end up with 0.5 moles of H plus in excess. And assuming that the solution volume doesn't change, that's going to give us an excess of 0.5 molar, and that's going to bring that down the pH significantly, okay? The pH is going to go. So we have overcome the limitations of the buffer. Buffers can only maintain their pH when small amounts of acid or base are added. So your blood has a buffer system. Yes? Do you guys remember the buffer system in the blood? If you took biology? The blood buffer, we have HCO3 minus in equilibrium with H2CO3. Is that ringing any bells? Yeah? I don't know. They may have written this as H2O and CO2 because that does equilibrate there. Okay. But basically you've got those two. Actually, I should put the water over here. You don't need to memorize this. Okay. So your blood has a buffer system because it's got HCO3 minus, it's got H2CO3. But if you were to inject your blood with a whole bunch of sulfuric acid, a strong acid, would your blood be able to deal with that? No. Okay. Buffer systems cannot, oh, here's another one. They cannot be made from a strong acid. So they cannot be made from a strong acid, nor from a strong base and the salt of its conjugate base. Or vice versa, rather. Why not? Why can we not make a buffer from something strong and strong?
Because it will not go the way.
It won't go the other way, right? You need an equilibrium that will be able to shift to absorb extra hydrogen and shift to make extra hydrogen. These go one way. Yes? Buffers have to have an equilibrium. AP Chem only, we're going to cross that out. And we're going to cross this out. And we're going to cross that out. Okay.
Like even the exercise.
Huh? I'm just trying to see if there's any exercises that have it. I don't think there are any, so I think it's okay. Okay? And if you were away yesterday and you did not check on Teams, the homework was 5.3E and page 64, number 3 and 4. That was to prepare you for your quiz on Friday. But I would like you, because that was a real day and it happened, today you're going to do pages 85 and 86. And if you did not do that, if not done, catch up on 5.3E and page 64, number 3 and 4. Okay?
You never. Yeah. It was really. She retired early because her dad sold. So, yeah, so she retired early at age 43. She was about 10 years older than I was. And I was like, not ready to be like this. I was like, I'm not an adult yet. I'm not a grown up. Yeah. And sometimes even now, I'm like, what am I supposed to do? Yeah, you'll be able to figure it out. I mean, that's the one thing we do. That's the one thing we should do. So bad at doing things. How can they not look it up? You guys are probably okay. Like they have no idea. Yeah, they're like, oh. Yeah, and I'm like, oh, I think that was. I work in a different way. I'm surprised. Yeah. No, no. Yeah, or I think one time I ended up with this after I never kept it. Else. What is happening? Yeah. Pass the moment. Good. Yeah.
Oh, I mean, I feel just like.
No, you need to fix it.
Oh.
That, I mean, then you won't, you're ready for the paralysis. I mean, honestly, I would be okay with that, but I think it's money wise for me to do that because this quiz lets you know what you're testing and it's a test where lots of stuff. Yeah. Really want to know where you're falling from. Okay. Yeah. That's next Friday. Okay, that's next Friday. We'll make it happen. Thank you.
Does that mean we only have 1 week to do electrochem?
We'll just, yeah, and we're gonna do a lab, so we won't really do very much electrochem.
Is it because we moved a bit too slowly?
Yes,
Well, it will.
it's because I gave you guys review days and stuff.
Oh.
Yeah.
We're not supposed to give us review days?
Well, not if we want to finish the course. Yeah.
What? Canto's so long though.
What's that?
Canto's like a big word.
It is a big course.